In this video, I want to look qualitatively at the position function for oscillatory motion. So if you've been through rectilinear motion and circular motion, you may be wondering why we keep going on with this. Well, there's a couple reasons. The first of all, I really want to drill in the fact that what we're dealing with is a vector function of time. And that's something that may be new to a lot of people, that you have some function where you input a time, and when you output is a vector, in this case, that shows the location of an object. So this idea of a vector function of time. But the other part of it is I want to start practicing how to visualize different types of motion, how to visualize rectilinear motion, visualize circular and oscillatory motion, but also how to visualize these vector functions, to be able to see this vector move and change as a function of time, and to be able to see it in your mind as you correlate it with your visualization of an actual physical system that's moving. And so finally, the other point of all this is simply practicing visualization, because that's such a key point in solving so many of these problems. All right, so oscillatory motion, what we're trying to visualize in this case is, say, the motion of a mass on a spring. I've sort of drawn a picture here of a mass that I've stretched out to some distance, and I'll let go, and it's going to, the spring is going to pull it back. I've put here my coordinate system 0 is at equilibrium, the point where the spring does not exert any force on the object, and so it would just stay at rest here. And then, so as the thing moves, the spring compresses until it gets, this is the other limit, and then it comes back, and it oscillates back and forth between these 2 points. And so you can visualize in your mind this mass on a spring oscillating back and forth between sort of 20 centimeters and negative 20 centimeters on this axis, which we said is one dimension, and we've labeled the x-axis. So at t is equal to 0, we say the particle, I'll get a different color here, our mass is at 20, and then we're going to look at each delta time to be 0.2 seconds, we're going to say. And so at delta t is equal to 0.2, it's moved just a little bit. We're going to say this is about 18.5. And then at 0.4 seconds, it's moved to about 14. And then another 0.2, it's moved to about 7.5. And then it's at 0. And then it duplicates it in the negative axis, comes out to about negative 0.75, then to about negative 14, about negative 18.5, and then negative 20. And then it just comes back. Each 0.2 seconds, it looks to be in exactly the same place it was before as it completely retraces its step. So it's covering all of the space between positive 20 and negative 20 centimeters as it oscillates back and forth between these 2 points. But for each 0.2 seconds, this is the snapshot of our motion diagram, and we find that it doubles back on itself, and each snapshot, as it oscillates back and forth, we see it come in exactly the same place. All right, so let's look at what the vector function in time looks like. Since it repeats on itself and it travels all the same ground, I'm not going to write my vector function on my axis itself. I can translate my vectors, and so I'm going to move my vectors off a little bit so we can see them. So this is r at 0. It is equal to 20. It has a magnitude of 20 centimeters. It's along the positive x-axis. Everything's in centimeters here. And so at t is equal to 0.2, that's going to be here, and we see that it's slightly less. So r at 0.2, we said about 18.5. It's also pointing along the positive x-axis. And so at point 4, our vector is shrinking. Now, this is a magnitude of about 14 centimeters along the positive x-axis. And then at point 6, it's down to about 7.5. R of point 6, we say 7.5 along the positive x-axis. And at point 8, it's seconds, it's at 0. R of point 8, 0. And then it starts to move off at R of point 10, R of 1 second, point 10. R of 1 second, it is now has a magnitude of 7.5 centimeters, pointing along the negative x-axis. And then at t is equal to 1.2, 1.2, it is equal to, it has a magnitude of 14, pointing along the negative negative x-axis. Then at 1.4, it has an 18.5 magnitude along the negative x. And then R of 1.6, then 20 along the negative x. Now I'm not going to just write all of that out, but I want to continue to write my vector function. If we go to 1.8, then it starts coming back. Now I said each snapshot of the motion diagram exactly overlaps where we saw the motion diagram before. So now it's the vector function starts shrinking back to 18.5, then 14, then 7.5, then 0, then 7.5. 7.5 seemed to be a little different length there. And then 14, then 18.5 now along the positive x-axis, and 20. So now I have time sort of increasing as we go down here. But this is now what the vector function in time looks like of an oscillating function, where I've started it now at the largest positive maximum value. It starts shrinking, but still pointing in the positive direction until it comes to the origin. Then it starts increasing in the negative x direction till it reaches its maximum amplitude in the negative x. Then it comes back to 0, and then going back, increasing in the positive x till it comes back to where it started. And so now come back, just take a moment to visualize what's happening. Now go back and imagine this mass on the spring oscillating back and forth between positive 20 and negative 20. And now imagine following that mass on a spring with the yellow position vectors. At each point in time, the yellow vector is pointing, giving the location of where that object is. That is our position function, giving us a vector function of time, telling us the location of the object at every time.